when last we left our heroes, they were talking about trailer brakes and the fact that trailer brakes are based on the inertia of the trailer that is pushing the truck along in front of it. And when the trailer continues and the truck starts to stop, that activates a mechanism inside the hitch, and that engages the trailer brakes. That's one of the places we use inertia. We use inertial braking in seat belts. Now, I don't know how an inertial brake in a seat belt works, but you know that if the car is going forward, or if the car is starting to slow down, your seat belt locks. That's because it's an inertial brake. So, we've been doing equilibrium in a matter of speaking, but we haven't talked about it formally. So, equilibrium is a concept in biology. It's also a concept in physics. And this is where an object is not accelerating. So there are two conditions under which an object is not accelerating. One, it's at rest. Acceleration is equal to 0. What's the other one?
It's at a
constant velocity. Velocity, be careful.
Sorry.
It's okay. It's at a constant velocity, and then there's no acceleration, and then we consider it to be at equilibrium. Equilibrium means the forces on it are balanced. So when we do the sum of forces, we get 0. They cancel one another out. We can be in equilibrium on one axis and not the other. That's going to be an important thing that every time we look at a situation now, we're going to kind of ask ourselves, is this thing accelerating on this axis? Is it accelerating on that axis? You know, how do we prove that? And of course, we prove that using the thing we started off using in 4A, which is sum of forces! I feel like I should be saying Captain Caveman there. Yes, indeed. How do we determine equilibrium? We do a sum of forces on the x and the y. And when sum of forces x equals 0, it's in equilibrium on the x. If sum of forces on the y is also equal to 0, it's at complete equilibrium. It's not accelerating. It's either at rest or it's moving with constant velocity. So now we're going to get into Newton's second and third law. The first law was the law of inertia. This follows out of the stuff we talked about with inertia, the fact that inertia is directly proportional to inversely proportional to mass. The acceleration of an object is directly proportional to the force, and the acceleration of an object is inversely proportional, I'll get it right yet, to its mass. So what this gives you is F equals ma. Did you guys use this in physical science? Did you do F equals ma problems there?
Slightly.
It depends on who you had, and the last time I taught physical science, which was 12 years ago, F equals ma was not in the standards for physical science, but the kinetic energy and potential energy equations were, so we didn't do F equals ma, we did kinetic and potential energy.
We did a little bit.
Okay. And that's fine. I mean, F equals ma is not hard. It's pretty basic, but there are a few common pitfalls. The first thing to note is that this is sum of forces. So you didn't talk about that in physical science because you didn't have that concept. You just said, oh, well, you know, there's a 10 Newton force acting on a 5 kilogram object. What's its acceleration? But now what we have to think about is that F is in fact the net force on the object. And you know how to find net force. You've done it in situations where you've got, 3 or 4 or 5 forces acting on one object, like a succulent stuffed turkey, for instance. The sum of forces is going to be a vector sum. So it's not just one force or another. You have to consider every single force acting on the object. Now we're going to do the sum of forces step that we did in 4A, but to that we're going to add the fact that whatever that net force is, which we've been finding, equals the mass times acceleration of the object. So we're going to do the 4B sample problem together, and, well, you know what? Before we even do that, let's do a different one. Let's say we've got an object hanging on a cable, and we are told that this object is accelerating upwards, so it's being pulled upwards at 3.5 meters per second squared. What do we want to know? We want to know the force of tension on this thing. Did I mention that this object has a mass of 11 kilograms. Okay, so we have an 11 kilogram object on a cable accelerating upwards at 3.5 meters per second. What is the force of tension on the object? Where do we start?
Force of gravity is 11 kilograms, right?
11 kilograms is a mass, not a force.
Well,
Yeah.
So, but the gravity is equal, the force of gravity is equal to mass times gravity.
Gravity, mg. Okay, well, how about this? We start with the sum of forces. Okay, so based on what we're told, let's start with the sum of forces on the x. Are there any lateral forces here?
No.
Nope. Sum of forces on the x equals 0, and that equals ma. Therefore, acceleration on the x-axis is 0. Okay, fine. That's done. Now we're going to go to the y-axis, which is where the juicy stuff is. So here's something that I want you to get used to, and this is going to be really useful when we go into C and D. I'm going to write this out as two equations, and I'm going to set them equal to one another. Because there are two things here that are true. Sum of forces on the y is equal to the mass times acceleration. Sum of forces on the y is also equal to all the forces up minus all the forces down. Okay, well what that means is that all the forces, and I can, clarify that a little bit. That would be the force of tension minus the force of gravity. Well, what that means is that, and this is just my personal habit, I always put MA on the right. You don't have to. It does not matter. Force of tension minus force of gravity equals mass times acceleration. Oh. So, now we got something we can work with. Questions?
Oh, that's mass times acceleration.
Yeah, that's mass times acceleration.
Oh, so it was mass times, I thought that was
Now, what is force of gravity equal to? Mass gravity. So Ft minus mg equals ma. And I'm going to shrink this a little bit. So, are we ready to solve for force of tension? Yeah. Force of tension in this object is equal to ma plus mg. All right, so we've got this. We've got our numbers plugged in for MA, our numbers plugged in for MG.
That results in 146.41.
We only have 2 sig figs, so we'll call this 150 newtons is the force of tension in this cable. Now, is there any way that we could clean up or simplify this step?
You could take 11 out front.
We could factor out the mass. So, one alternative pathway, and actually that would really occur in the step above, but one alternative pathway there is to say that Ft equals mass times A plus G. And that just, it slightly simplifies your calculation. There will come points where being able to factor out that mass will be useful in terms of some rearrangements. So, questions on that? Let's do 4B together. I wanted to do a force of tension MA problem with you because those are something that are always a little bit tricky. So I just wanted to get that out of the way. And that wasn't too hard, but it gives you the sort of mental template for them. So Roberto and Laura, are studying across from one another at a table. Laura slides a 2.2 kilogram book towards Roberto. Roberto, if the net external force acting on the book is 2.6 newtons to the right, what is the book's acceleration? All right, so we have the book. It has a net force of 2.6 newtons that direction. The mass of the book equals 2.2 kilograms. So here we were given the net force. So sum of forces equals ma, and we want acceleration. So net force divided by mass equals acceleration. 2.6 newtons divided by 2.2 kilograms gives us 1.1818181818. So 1.18 blah 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 equals acceleration. And you would have to say to the right, because that's going to be in the same direction as the net force, and they said that was to the right. How many sig figs do we have? Just 2, so this becomes 1.2 newtons right equals acceleration. Does that make sense?
What do you mean? The units would be 1 point.
Oh God, I put newtons in. Durr. Try meters per second squared. My brain's in newtons, sorry. Fell here to change gears. I mean, this one's too easy. That's why I did the force of tension one with you. Do you want to do one more? Let's do one more that I just sort of make up, and let's talk a little bit about, because this is the other kind of problem that tends to give people fits in a little bit, which is sloped surfaces. Yeah, everybody hates sloped surfaces. So we've got a ramp here. We have a 21-degree angle with the ground. And we've got an object on that ramp. Mass of the object is 15 kilograms. You have been tasked with pushing this object. You know, let's not talk about the fact that your arms originate directly from your pelvis. That's kind of weird, but whatever. You've been tasked with pushing this object up the ramp. And the force that you are exerting on this thing, so the force of you, actually, let's make that 150 kilograms. Let's make this worth your time. We'll make it 155 so I can get an extra sig fig in. Make that 21.0. If I'm making it up, I might as well give myself a few extra sig figs. It is a heavy box. Poor you. So the force that you are exerting up on this thing, and I'm gonna make this up off the top of my head. So we're gonna have a trick at the end here. So the force that you're capable of exerting on this box, let's say, is no, you're not that powerful. We'll say 426 newtons. Okay? Too late, I wrote it down. So the question is, will this box accelerate up the ramp or down the ramp? Well, the only way to figure this out, and we've said that this is a frictionless ramp, so there is no force of friction because we're not ready for that. Perfectly smooth ramp. So no friction on the ramp whatsoever. I don't know how you're walking on it, but we're not going to talk about that because this is high school physics, so we like to ignore these things. So you have magnets, and it's a perfectly frictionless metal ramp. Very good. Thanks for the fix there, Jeremy. Okay. Well, let's draw in everything else here. Whoops. So we have F sub g, which is equal to mg. We know, because we trust in analytical geometry, that angle is 21. We know that this is FGY, and this is FGX. Oh yeah, and there's a normal force on the ramp. On the perfectly smooth but magnetic ramp. I love outrageous physics problems. All right, so where do we start? Well, we start, as always, with the sum of forces, don't we? All right, were we told that the object is sinking into the ramp or levitating up into the air? Nope. Therefore, it's at equilibrium on the y-axis. But just for good form, we would do this. Sum of forces on the y equals 0. And that's equal to all the forces up minus all the forces down. So it's also equal to Arg. Hold on. Let me just do this. Sum of forces on the y also equals m times acceleration on the y, which is also 0. And of course, this is normal force. This is FGY. And we don't really have to go any further with that one right now. We've just kind of set that aside. We've proved that we know that the normal force is going to be equal to the sum of the force of gravity on the y-axis. Only on the y-axis. Do not make the mistake of saying that Fn here equals Fg, because it doesn't. It equals a portion of Fn, or of Fg. All right, so we've kind of done this little note to self, and we're going to set that aside. The y-axis is obviously where all the, oh, good God, Moser. Who let me out of my cage this morning? The x-axis is obviously where all the action's happening. So sum of forces on the x is equal to mass times the acceleration of this object on the x. Sum of forces on the x is also equal to all the forces, you know, and how we designate this, up ramp, down ramp.
Would it be a push of u minus force of gravity on the x?
And it is, yeah, exactly. Down ramp. Well, that's, yes, force of u minus force of gravity on the x. So mass acceleration on the x equals that. Now, max, yes. Now, we know what the force you're exerting up is. What is the expression for the force of gravity on the x? mg times sine of 21. Correct? We good with this? Okay. If you're not good, holler. Don't be brave. Okay, I'm gonna. So, what we're interested in, of course, is what?
F of u.
No, we know f of u.
Whether the box is up or down.
We want to know how it's accelerating.
Acceleration.
So we're interested in solving for acceleration on the x-axis. And to do that, we have to divide both sides by the mass of the box. So we'll just get rid of that. So now we have acceleration on the x-axis is equal to 426 newtons minus, and I don't know the answer to this. I don't know if you're winning or not. Minus 150 was 155 kilograms times 9.81 meters per second squared times sine 21, the whole mass divided by 155 kilograms. I'll pause the video to give you a chance to calculate it and give me a chance to calculate it. Okay, so we've got an answer. What does our answer mean?
We lost.
It means...
We're getting crushed.
That's what it means. I know, wasn't it? It means that this box is pushing you down the ramp. You're not exerting enough force on the box to get it to move up the ramp. You will have other problems like this. I think I put one of these on either a FIP or a test, or I give you a ramp problem. I tell you, you know, this is the amount of force that you're able to exert up. Is it pushing you? Are you getting it to move, or is it moving you down the ramp?
This is reminding me of.
I mean, that box is
I can't remember.
So the 4B book are all assigned, and I'll have the worksheets available for you to, yeah,
Can you go back to that actually?
absolutely.
I'm a semi-Greek mythology buff.
I forgot to resume recording. We were talking about why, where that sign came from, that FGX is just a component of force of gravity, not the whole thing. And we can draw it up here, we can transpose it parallel to itself. And of course, I didn't know this when I was drawing it, but the force of gravity on the X was actually greater than the force you're exerting on the box. So, other questions? Now, the fact that this is a negative, this is worth mentioning. You know, we all saw that negative and immediately went, oh, it's pushing you down the ramp. Well, you know, we had the force of gravity on the X as our negative. We had the force of U as our positive. There's nothing to say that we couldn't have flip-flopped that and drawn the ramp the other direction. We could have, we could apply a Cartesian system, we can apply a non-Cartesian system. Actually that's backwards from a Cartesian perspective. Cartesian perspective, this would be our positive, this would be our negative, but we didn't make it that way. We used the up ramp, down ramp. So, just be careful because sign is a proxy for direction, but you have to make sure that you're consistent throughout a problem. So.